So it's my pleasure to introduce our second speaker, James Freitag, and he'll speak about strong minimality for Painlevé equations and Fuchsian equations.
Okay, yes, this is sort of a talk on two topics, but I'll say kind of similar things about both. And I should say, even though I didn't write it here, it's the first topic on Painlevé equations is joint work with Ronnie Nagloo, and the second topic on some Fuchsian equations is joint work, again with Ronnie Nagloo, but also Guy Casale and David Basque-Sanz. Okay, so the one thing that I'll talk about the whole time is this notion of strong minimality, and so I try to define it in terms that I think anyone can understand, even if it's a little bit unfamiliar to some people. So I'm taking the solution set to some algebraic differential equation, just in one variable in this talk, of some order n, over some differential field k, and in this talk always characteristic 0. So then this set is strongly minimal, the notion we're mainly considering in the talk, if whenever you take a solution to the equation and any differential field that might be bigger than k, but also k itself, so already you have to think about that, then the transcendence degree of the solution and its first n-1 derivatives is either 0, so it's algebraic over k1, or it's as big as it can possibly be, given that it satisfies this order n equation. Okay, so right, and so it's just a phenomenon for nonlinear equations. No linear equation can have this property. Okay, so if you have some question about it, let me know. Yeah.
Two comments. Yeah. One, what you define as minimal, strong minimal, and
wait, I'm sorry.
That's not strong minimality. That'd be minimality. And if n equals 1, you could do it for linear equations.
So I guess you have to add degree.
Okay, yeah. So I think it's best to think about it in these terms for this talk. It won't make a difference for the equations that I'm thinking about. Yeah, but right. I mean, but you know, Tom, I am allowing any solution to the original equation.
Yeah. Like if an order 0 equation is defined a finite set, it's still set.
Okay. So it's not an order 0. N is bigger than 0. So in this talk, okay. And you can see also this is not an interesting condition. This is pretty much not an interesting condition when n equals 1. And okay, and like Tom says, you need to think about a little bit about, say, like, some other considerations. Maybe I should call this minimality for various reasons. Okay, so this is a kind of functional transcendence result itself, but one thing which it's not completely obvious to people who didn't study the notion is that it's useful for proving even more functional transcendence results. And it pretty much, well, as far as the work in this talk, I mean, the reason that that's useful is this point here, that model theorists have developed a certain kind of classification of strongly minimal sets, which I won't really talk about much because it's a topic itself. Okay, so I think most people have heard of Painlevé equations, but let me just quickly say some things about them, even though I think maybe half of people here have heard me say something like this before. Okay, so it starts, I guess, in the 19th century with this question: which equations of this form have the property that the movable singularities of any solution have to be poles? And this came to be known as the Painlevé property, and A movable pole, well, okay, when you solve an equation like this, maybe you integrate some function and an arbitrary constant appears. And it might even appear, say, like this in the denominator of a fraction. And so the location of the singularities of the solution depends on the value of that arbitrary constant. And that's what we call movable singularity. That's a movable pole, of course. But you could have something worse, since I'm thinking about, we're thinking about complex analytic functions. So, so a function like this has a worse kind of singularity at t equals c, because you have to take a branch cut in order to define it as a complex analytic function in the neighborhood. Okay, yeah, and so solutions of linear ODEs have no movable branch points. Okay, earlier, Poincaré and Fuchs proved that any nonlinear order 1 ODE with this Painlevé property about the movable singularities could be transformed in some way, which I won't talk about, into just very specific kinds of order 1 equations. Okay, and well, at least someone thought it would be super impressive if you could understand this in order 2, and that's what Painlevé and then people who came later began to do. Okay, so Painlevé's work was a little bit incomplete, and these other people filled in some of the gaps. Okay, so that's where these equations come from, but it's not exactly the kind of thing I'm considering in this talk, although it's related. So here are the equations. They look horrible, and these Greek letters here, these are complex parameters. Okay, so these range over any complex numbers. So they're really 6 families of equations. Okay, and so here's the problem. Here's a general problem that, well, some of us have been interested in solving. So the problem is in blue. So to classify the differential algebraic relations between solutions of Painlevé equations. Okay, so if we're, and I mean it pretty generally. So just given some solutions y1 to yn from any equations in this family, maybe different equations, who knows? What are the algebraic relations between the solutions and their first derivatives? You don't have to think about the second derivatives, of course, because each of them satisfies an order 2 equation. And we only really need to think about generic solutions because there's a complete classification of algebraic solutions to Painlevé equations and solutions which satisfy order 1 equations. So that's been completely classified in each of the families. And this notion, strong minimality, is a key role in the way that we think about this question. So I mainly just wanted to tell you what's known and what's conjectured about this question because I think it's interesting. But first, I'm going to try to explain what I think is a new proof by Ronnie and I of strong minimality of this equation, at least when the coefficients are generic, which some of you probably realize is the easiest case in a certain sense. Okay, so here's the 6th Painlevé equation, written out again. Looks horrible again. And it turns out, though, that it's related to a certain kind of equation on an elliptic curve, at least sometimes. So if you take the elliptic curve, which is the closure of this equation here, then there's something called the Manin map. It's given by this formula here. You have to be careful where you get the formula from which paper. It's wrong in some places. Okay, and so this is called the Manin map, and it has some special properties, but I'll say something about it in a moment. Okay, so again, here's this Manin map, and if you set it equal to 0, so you set this left-hand side equal to 0, and then, well, you notice that, well, we have this algebraic relation here, so we may be able to, get rid of these y's and express them in terms of x, and you can. If you do that, and then you solve the resulting equation, it's this. And it should look familiar because this is Painlevé 6, but with certain values of the parameters plugged in for alpha, beta, gamma, delta. Okay, so it's these parameters right here. Okay, and I don't have time, and I don't want to say a lot about Manin kernels, but one thing is that Rashofsky showed that equation is strongly minimal, and also like many more general ones in the 90s associated with higher dimensional abelian varieties. And this, we're going to try to use this. Okay. So here's how to use this. So this family, it's not just a bunch of separate equations. There's some structure on the family which you can exploit. So you can think of the family as being a collection of equations over each point in C4, that alpha, beta, gamma, delta. And it turns out that there's a group which acts on C4 by transformations, so that there's a birational transformation between the solution sets of the corresponding fibers. Okay, and so here's the group. It's not so important exactly what it is, but I'll just point things out about it that you need to know. So it's generated. The group is generated by these elements here. So the first three just say that you can permute the coordinates how you like, and and this one says that basically you can, because you can permute the coordinates. This one says that you can change the sign of 2 of the coordinates at a time. And this one says that you can add 1 to 2 of the coordinates at a time, basically. All right. The point is that the orbit of this group in C4 is Zariski dense, and that can be used. We will use it. Okay, so let's see how. Okay, so I'll try to give a sketch of the proof without quite all the details. So when I write P6 of this, I mean the equation with those parameters. So suppose it's not strongly minimal, and the parameters are generic. Okay, so now we have to use something special, which I'm not going to really justify, but there are results from model theory which say that you don't have to think about arbitrary differential field extensions, K1. You can think about just ones generated by solutions to the same equation that you're considering. Okay, so it's pretty useful. It's useful in this case. And so non-strong minimality is equivalent to this property here. Okay, for some n, for some number of solutions to the equation, we don't get a multiple of 2. We get this odd number. Okay, for the transcendence degree of the differential field generated by the solutions over the field where everything is defined. Okay, so if that happens, that means that there's a differential polynomial with coefficients in this, which vanishes on what, if you're, say, speaking this kind of language, you might say is a co-order 1 differential subvariety of this differential variety here. I mean the n-fold product of that equation with itself. Well, okay. Now, for I guess in model theoretic language, it's true that the type of this 4-tuple here has to imply the existence of this variety here, okay? And so you have to just ask yourself, well, I mean, what are you using? And by type, if you're not a model theorist, you can just think the isomorphism type of the differential field generated by these elements here over Q of t. Those elements there are constants, so it's just the field generated by those. Okay, so, but then, well, okay, it's true that the definable subsets of the constants are given by Zariski constructible subsets, and we're over Q in this case. And so if that type is going to imply something, then by the compactness theorem, there has to be just some Zariski open subset, because it holds at the generic point. So there has to be some Zariski open subset, such that for any points in that Zariski open subset, this V is what we call a co-order 1 subvariety of this equation here. Okay, so there's some specialization principle here, which has to happen. Okay, well, okay, but this open set here hits the orbit of that Manin kernel because it was Zariski dense, and strong minimality makes having such a variety impossible. So it's a contradiction, and the generic Painlevé 6, it has to be strongly minimal. Okay, so this is the, I don't know, kind of style of, I guess you could call it like anti-specialization argument that you can find a lot in, I think at least in starting from the work of Ronnie and An and Pillay on Painlevé equations. Okay, so let's go back to the main problem, and I'll tell you what's known about it, and then I'll tell you at least, I guess, my conjecture on it. I have no idea if it's right, but okay. So the general problem is to classify differential algebraic relations between solutions of Painlevé equations. Okay, so there's sort of 3 things you have to worry about. The first one is algebraic relations between solutions of a single, like fixed Painlevé equation, like the same equation with itself n many times. You can see how strong minimality is related to this, of course. Okay, and so there's now very complete data, like this question is completely answered in the case of generic coefficients. The answer is there are no algebraic relations. But for instance, like Painlevé 6 for generic coefficients, it was only completed last year by Ronnie. And for non-generic coefficients, there are partial results, but I would say there's very incomplete data. I mean, it's understood which fibers are strongly minimal. In some cases, there's proofs of triviality by Ronnie and me in some cases. But little's known about that problem in general. Okay, the second kind of algebraic relations that you have to worry about are between solutions of equations from different families. Okay, and again, there's very complete data when one of the equations from one of the families has generic coefficients. The answer is there are no relations in that case, and that's in a paper of mine. And there's essentially no other cases known, although maybe I've sketched some arguments, at least related to Painlevé 2, which might give a good indication for how to attack the problem. But I don't think that there's a general method for most of the families for understanding this question yet. Okay, and then third, algebraic relations between solutions of equations in the same family but different coefficients. And again, there's complete data for one of the equations having generic coefficients. Okay, that's fine. Okay, it's also true that Painlevé 6 was only like just completed by Ronnie and I. And there's reason for this. I mean, because somehow progress in one of these areas, like number 1, lets you make a little more progress in number 3. And so the fact that Ronnie completed P6 is what lets us do this style of P6 problem. Okay, so I think that tells you what's currently known. Okay, and I would say here's the current conjecture. Okay, so that group of affine transformations that I gave are usually called Backlund transformations, and there's something similar to those for each of the Painlevé families. Okay, and so, I don't know, here's a conjecture. The algebraic relations between generic solutions of Painlevé equations are given by either Backlund transformations, algebraic relations within the orbit of the Manin kernel in P6. So I mean, within a given fixed equation, there's some algebraic relations coming essentially from torsion on elliptic curves, related to that at least in this case, but that's understood. And 3, some of the different fibers in the orbit of the Manin kernel in P6 could have isogeny relations between them. So, okay, and so in particular, if this is right, then there's no algebraic relations between pairs of equations from different families. There are no known such relations now, and what we've proved is that there's no relations when at least some of the coefficients are transcendental, but there's nothing known for, I think there's nothing known in general that I know of for algebraic coefficients. Okay. All right, maybe it's a good time to say if you have, does anyone have any questions on this? Because I'm going to slightly switch topics. Okay. Yeah. Okay. So yeah, it's a good question. So, I mean, the conjecture's been, it's been verified in all the in the cases where the coefficients are generic. So, I mean, the conjecture can be wrong, but I mean, it's at least generically true, right? I mean, it's true when it's basically you can show that it's known in various cases where you have at least one of the coefficients a transcendental number. Okay, so nothing's known, say, for cases where all the coefficients are algebraic. It's also true, like, for instance, okay, I mean, I don't think this is written anywhere, but I've said it in various talks. I mean, if you could prove that Painlevé 2 has this property that people have studied called differential completeness, it would follow, lots of other cases would follow from that. So there's lots of plausible, there's lots of things that are plausible that probably I would guess are true that would imply this in various cases. But yeah, I mean, yeah, maybe it should be said, like, in a certain sense, if this is wrong, I wouldn't be so shocked, but I think it's true. That's why.
And also you mentioned that the generic case should be easier.
Yeah.
And so I should know why. Well, I don't know why.
Well, okay, so essentially I think this is driven by the fact that we understand the structure of the solution sets in the generic cases of Painlevé equations sort of completely from the work of Anand, Pillay, and Ronnie Nagloo, and then later work that Ronnie did on his own. And so somehow that knowledge can be, it's that knowledge that you're repeatedly leveraging, I would say, that really gives you that the ability to attack the generic case as opposed to like the special case. So yeah. Sure.
So there is this Nagloo decoupled beyond the scene, and it's what you're saying more or less. It is as big as possible in the generic cases. So there are some specialization results for this decoupled. You can not precise this result with the Hilbert theorem version of decoupled.
Well, okay, good question. It's probably hard to answer that question. I maybe. I mean, yeah. So certainly that's true. But somehow, somehow I don't know of. Okay, so for instance, like results like that would you can use that, I think, to detect, for instance, like for which coefficients could there be solutions to the Painlevé equation that satisfy some order 1 equation. Yeah. But I don't know any examples where, for instance, you can use that to show that there are literally no algebraic relations between solutions of a fixed equation, besides at the generic point. So yeah, so if something like that can be shown, then I think it can be very usefully applied to solve cases of the conjecture. Yeah, but okay, so maybe I'll move on then. All right, so I'm still talking about strong minimality, but now about Fuchsian functions. And just let me say something about, I guess, like motivation for these problems, or why some people study them, at least besides, proving strong minimality results is kind of a central topic for model theorists doing differential algebra. But in this case, I'd say people also have thought about it in a slightly, for other motivational reasons. So if you have two algebraic varieties x and y, and some analytic map between them, it's a general problem. Okay, the map shouldn't be polynomial or rational map or something. It should be analytic but not algebraic. It's a general problem to understand which algebraic subvarieties of the domain get mapped to algebraic subvarieties over here. Okay, that doesn't happen most of the time with an analytic map, so you can call pairs of algebraic subvarieties which have this property bi-algebraic for the map. Okay, and various cases of this problem have been solved, and I think it's at least part of the motivation for what Casale, myself, and Ronnie Nagloo did for Fuchsian functions, and I'll say more on that in a moment. And our approach to this, to trying to solve this problem for a certain analytic function, uses strong minimality. And of course, I guess probably many of you know there's other approaches to this problem, other approaches which have been worked on much more actually, via other tools for model theory, coincidentally, like O-minimality. Okay, and also for model theorists, certain kinds of Petershill-Starchenko results as well. Okay, so let me try to define things, since I won't assume you know what these functions are. Okay. All right. So I want to take a discrete subgroup of SL2, and it acts on the upper half plane in the natural way. Okay. So if you take a point in the upper half plane, this is a discrete group, and so it has, its orbit has no limit points in H, but there could be limit points on the boundary, and in fact, I want that to be the case, and so this, say, first kind here means that every point on the boundary of the upper half plane is a limit point of this group. So, so you can be thinking of something like SL2 of Z, where the, if you like, where the map of the fundamental domain gets more and more compact as you get close to the x-axis. Okay, and the other assumption that we're going to make is that, well, if you take the quotient of H by gamma and compactify it, it's a Riemann surface, so it will be some algebraic curve, and we want it to be genus 0, and at least at the beginning. This will change. Okay, so, all right. So it turns out that in this case, yeah, let me just say about a way of notation, that the map from h to this curve, I'll write by j gamma in this way. Okay. So this is an analytic function, and it satisfies a nonlinear third-order differential equation, which, I'll write in some example. It's been studied by various people now. So this thing here is kind of horrible looking. It's this Schwarzian, and in general, for any such gamma that we've considered, this thing here is a rational function of y with coefficients in C. So, like here's the J function associated with elliptic curves, and Tom Scanlon and I studied this equation, I think, from this perspective. Okay, so, so it's a conjecture of Painlevé that the transcendence degree of y and its first and second derivatives in this case that I'm talking about is either 0 or 3. So it's exactly the notion we've been considering. The transcendence degree is either 0 or it's as big as it can possibly be. Remember, it satisfies this order 3 equation. Okay, so let me just tell you the story because I think it's like amusing, at least. Okay, so Painlevé eventually claimed to prove this result. That didn't work out because he used this thesis of Drac, Jules Drac, and it wasn't right. So the theorems in it that Painlevé was trying to use weren't true. And the weird thing about that, or the reason this story is amusing at least, is that there are letters of Painlevé and Vessio back and forth with Cartan pointing out these flaws. So, I mean, and this is 1898, and this is only a few years later. So it's not like he didn't know about this. Okay, so he used this to prove these results. I think, use it to prove these results, not to prove these results. Because he basically thought that Drac's theory would be put on some sort of firm foundation to make the theorems true, at least in a way that could apply to the special case he's considering. And there were like lots of other funny things written about this at the time. Like, so for instance, Louville wrote that the first Painlevé equation doesn't have this property, but he was wrong, of course. But I mean, I guess nobody knew at that time because there weren't any correct proofs for or against that. So I don't know. So there was some like weird controversy in French mathematics over this. So of course there's a whole separate story on Painlevé equations with regard to this kind of thing, but for the functions we're considering, I think the most notable result is Nishioka's. And he proves this when K is C of T. Okay, so not for extensions, but just for C of T. It's a nice argument that is actually very understandable. You think about the action of the group. And so with Guy and Ronnie, we proved the general result. And so for the rest of the talk, the kind of questions that I want to consider, the sort of meta question is something like this. Are there like soft generalizations of this result? And so I mean the kind of generalizations that where you can deduce, say, strong minimality of other things from our result in a way that doesn't require going through the whole machinery of the result, and just maybe uses a kind of specialization argument or something similar to our proof that Painlevé 6 is strongly minimal for generic coefficients. So some kind of result like that, and I won't probably have time to give details of proofs, but okay. So let's now. So again, we're taking a Fuchsian group of the first kind. not necessarily genus 0. And so this, right, I mean, the compactification of this thing here is some algebraic curve. And it could be defined with various coefficients, but in the case that it's defined over Q, so coefficients in the algebraic closure of Q, we'll call it a Bailey surface. Okay. All right. And so the so the result that we're going to use is one of Bailey that proves something strong about classifying Bailey surfaces. Okay, so there are two cases. So I'll try to say exactly what there are. We say that this gamma is co-compact. I mean, so that's if the fundamental domain for the action of gamma on H is bounded in the upper half plane, and in that case, okay, so I'm using C gamma for the algebraic curve corresponding to this quotient. So this quotient is defined over Q alge, if and only if gamma is a finite index subgroup of some special group written this way. And I'll say what it is in a minute. It's what's called a co-compact triangle. Okay. In the non-co-compact case, things are even more particular. So if it's not co-compact, then this algebraic curve is defined over Q alge if and only if one of these things holds. Okay, so these are some particular choices of gamma. Okay, so sorry. Yeah, okay, so somehow I put this in a slightly weird order, but let me do this slide first. Okay, sorry. Okay, so I'm going to define these so-called triangle groups. So just as groups with generators and relations, yeah, and of course, there's three generators, A, B, and C. And here, alpha, beta, gamma should be some natural numbers or infinity. And if they're infinity, then the corresponding relation just doesn't happen. Okay, so there's three numbers A, B, and C, three generators A, B, and C with these group relations here, and you should have that. Oh, this should say alpha, beta, gamma. So I've made a typo there. Alpha, beta, 1 over, yeah, that should be less than 1. Okay, and if all that's fulfilled, then this is a Fuchsian group. Okay, and the point is that that you can even write down what the R is in that case. That rational function can be calculated. Okay. All right. So, sorry, now I'm going to go back a slide since oh, sorry, yeah. So this function here is what I'm calling that. So we're looking at the differential equation satisfied by this function, and that differential equation is this Schwarzian one with this R value here, and the R value, it can just be calculated from the alpha, beta, gamma. That's the only point, I guess. Okay, so the thing that we use is the fact that, I don't know why I put these slides in the wrong order, but the uniformizing functions of these triangle groups, they fit into the framework that we'd earlier considered. Okay, so they give genus 0 quotients. And it's not hard to see also that if you have two groups and one group is finite index in the other, then these functions corresponding to those groups will be interalgebraic. Okay, and so things are all set up. Things are all set up for what I would call a soft proof of strong minimality in this case. Earlier we had assumed genus 0. Here we're not assuming that, but we're assuming something different. We're assuming coefficients in Q-alg, and the reason that that's useful is that we have this theorem of Bailey that tells us that they're finite index in these things where we've already proved the result. Okay, and so maybe there's, I won't dwell on it, but the upshot is that you can prove the result in a straightforward way in this case from our result with no technicalities or anything like that. It's just a fairly soft proof modulo these results, which granted might be hard themselves. Okay, so, and I want to talk about, in the last couple of minutes, one more situation in which you can similarly give some soft proof of a functional transcendence result. So here's, for these groups, here's the equation given like this. And here, remember, alpha, beta, and gamma, they're natural numbers or infinity. And if they're infinity, then you get rid of them. Notice they're all to the -2. So that's infinity to -2, I guess is 0. Okay, and so, but you could ask in general, what happens if you consider the same equation, but you pick these things here to be arbitrary complex numbers, not necessarily integers. Okay. And you can do that. And so, well, here's at least part of the result that that you can prove. Okay, so if you have these alpha, beta, and gamma being so that the equation, the differential equation with the R rational function corresponding to those is not strongly minimal, you can do a sort of specialization argument, like I did for Painlevé 6, a soft argument to show that this equation here is strongly minimal when alpha, beta, and gamma are generic, when they're independent transcendentals over Q. But in this case, you can actually get more complete data. You can prove more. I'm not going to put the whole result on. I'll tell you why in a second. But if this equation is not strongly minimal, then one of the following has to happen. Okay, you look at these 4 complex numbers, and one of them has to be an odd integer, or you look at these quantities here, and when I write 1/2 plus L, here L is an arbitrary integer, and M is an arbitrary integer. And so this is in case 1, this means that this has to be equal to that for some L, and this has to be equal to that for some M, and this can be anything. Okay, and then maybe there's some additional requirement there. Anyway, I can't show you the whole result because it goes on for 15 rows, I think. It goes on, unfortunately. So it's a complicated exceptional set. And the reason comes from differential Galois theory, because you can relate the strong minimality of this equation to a certain associated Riccati equation having algebraic solutions. And that problem's been studied intensively. And this big table is essentially, well, okay, I think David wrote it out, but it comes from work of Kimura. Okay, all right, so maybe I should save some time for questions, but I'll say something about other things you can think about. Okay, so many people here know there's various approaches to these kind of, well, I didn't really use the words in this talk, but people call this kind of bi-algebraicity problem, an Axelinden and Weierstrass type problem. And there's a big approach to this using O minimality, and and we're doing something. We're just doing a different approach in this work. I think it's an interesting question about whether there are some settings in which a combination of these methods would be useful. I don't know. I think it's interesting to ask what, so these people studying via O minimality, various groups have proved stronger results, which are called Axe-Shanuel style results, or just Axe style results. And I think, it's an interesting question to say, can you prove these style of results via these methods? I also don't know. And then finally, people studying via O minimality have also proved things about generalizations to higher dimensional spaces with bigger discrete groups acting on them. And I think it's interesting to consider that as well. Okay, and that's it. Thanks.
Do you have any questions?
Do you know if anybody ever got Drax theory straightened out?
Well, I think it would be better to ask someone like he or David that question, and they could tell you what aspects of. I mean, it was some. I mean, as far as I don't understand this nearly. I mean, not even on the same level as say they might, or maybe even Ronnie. But I mean, it's some attempt at a certain kind of nonlinear differential Galois theory, and of course, that's also the kind of thing that they're generally working on. But to say what aspects of their current theory, capture which properties he was going for, I'm not the best one to systematically answer that question, but. I think the answer is probably, to some extent, but yeah.
Could you explain a little bit the connection between your approach and with the Schwarz list, which is more or less.
Wait,
You use some.
Sorry, I just didn't hear
There
that.
is an analogy between your equation and one with the Schwarz list.
In which list?
Schwarz list.
Oh, yeah. Okay, so I mean, there's so this is like the associated order 2 linear equation. Yeah, and there's right. So you can basically, in some ways, the theorem says that it reduces strong minimality to some condition about that associated linear equation. I mean, no Liouvillean solutions, and so and then you exploit the fact that things are known about that.
So continue that question. How does the Riccati equation come in there?
Well, so I mean, so there being there being no Liouvillean solutions to the order 2 equations related to there being no algebraic solutions.
No, but from how does the Riccati equation come into your setting?
Wait, what do you mean exactly?
It's equivalent. It's the same. All three are equivalent. So the equation is strongly minimal if and only there's no algebraic solution of the equality equation, and finally no Liouvillean solution.
Oh, I see what
Yeah, I mean that's essentially the proof of the theorem.
Yeah.
Boils down to being able to understand that equivalence, and then you have all this machinery from the detailed calculations that people doing Galois theory have done, and you can immediately port those over to strong minimality results for the nonlinear equations.
Okay. Would there be model theoretic content to knowing Max-Shanuel results instead of Axelinden and Weierstrass?
I think so. But also, I mean, yeah, maybe I should just roughly say something. So for for people who are just listening and hearing words that they don't know. I mean, so in this Ax-Lindemann theorem, you're trying basically to understand what kind of algebraic relations in the domain of this analytic map get sent to algebraic relations. But you could ask more generally what kind, even say analytic relations get sent to algebraic relations, and try to understand those. And that's kind of the flavor of the problem. I think the two are related. I don't have something concrete to say, but also I think you would have to understand various aspects of the model theory of the equations in order to prove an Ax-Shanuel type result. And so I'll just say something vague.
Any other questions?
What might be a simple example of an analytical map that does not preserve algebraic relations?
Oh, well, like the exponential map applied to each coordinate of the complex numbers, and so you ask yourself, well, so I'll write E bar from C to the n, and of course you're not going to hit the origin. So, I mean, you want to know what kinds of algebraic relations get sent to algebraic relations. It's not, I won't talk about how you prove it, but at least maybe you can see that if you have a Q linear relation between the coordinates here, it will be sent to an algebraic relation here. So, a linear relation with coefficients in Q, like sum Qi xi equals some complex number C. That can get sent to an algebraic relation here, but that's the only thing, in fact. So the algebraic relations which get sent to algebraic relations are very special. Yeah. In this case and in most others. In this case, they're also very special. If you take J gamma bar from, which is just this J function applied to each coordinate, then, and then the kind of result that we and other people are proving is that the only algebraic relations preserved that get sent to algebraic relations correspond to two coordinates differing by the action of an element in the commensurator of the group. So so in both cases, they're very special, discrete list of algebraic relations.
If not, let's thank James.